All right, so let's pick up where we left off last time, talking about these electron configurations. All right, so given where an element lives on the periodic table, we should be able to tell its electron configuration, which is a summary of all the different types of electrons in that atom. So if we take neon, for example, we're going to find neon on our periodic table. And remember, we had to cut up our periodic table into these different blocks. We got the S block, the P block, and the D block. And then all the way down here is the F block. And we can number our rows. For our S block, we're going to start at 1. For our P block, we're going to start at 2. And for our D block, we're going to start at 3. And for the F block, we start at 4. All right, so we find our element on our periodic table. Neon is the 6th element. 1, 2, 3, 4, 5, 6th element in that 2p row. So that tells me the last orbital in its electron configuration is 2p6. But then it's got to contain everything that came before it as well. So what's in front of this 2p row? If this is element 5, let's find element 4 is in the 2s row. So 2s2. And what's in front of 2s? 1s. All right, if we do the same thing for chlorine, chlorine's even further down on the periodic table. So it's going to contain everything that came before it, but the last orbital in its electron configuration will be the 3p5, because it is the 5th element in the 3rd row of the P block. And then it's got to contain everything that came before it. So what's in front of 3p? So if we're in, element 13, right? We jump to element 12. This is in the 3rd row of the S block. So that would be 3s2. And what's in front of 3s? 2p, right? So now we got to go all the way back to the other side of the periodic table, as if you were reading backwards in a book. We go from element 11 back here to element 10. So that would be that 2p row. In front of that is the 2s, and in front of that, the 1s. Okay? So this is obviously the bigger the element, the more electrons it has, and so the longer its electron configuration, right? This was chlorine here. What if I pick something all the way down here at the periodic table? Radon. It would have this ridiculously large electron configuration, right? So we have a way of summarizing these electron configurations, or rather abbreviating these electron configurations using the noble gases. Okay, so this is what we call the noble gas abbreviation. Oops. All right, and let's take these two elements as an example here, neon and chlorine. Since the larger elements contain the electron configurations of all the smaller ones that came before it, if we look closely, we see that this portion of chlorine's electron configuration is an exact match for the electron configuration of neon. All right, so what we can do for our chlorine electron configuration is we can summarize it by saying chlorine's electron configuration is whatever neon's is, insert neon's electron configuration here, followed by this extra bit, right? So it's neon's plus the 3s2 and the 3p5. Okay, so in brackets, we have this noble gas. What this is saying is insert, in this case, neon's electron configuration and then add on this extra bit to get chlorines. All right, so we can summarize our electron configurations of an element by using the closest smaller noble gas. It can't be bigger or it will have more electrons. But we can choose the next smallest noble gas and use that to abbreviate our element's electron configuration. Okay, so let's do an easy one first, and then we'll jump to one of the bigger ones on our periodic table. Okay, I want you to give me lithium's electron configuration using that noble gas abbreviation. Remember, helium is really in the wrong place. It should be right here as the second element in that 1s row. All right, but helium will be the next smaller noble gas, so you'll use helium to abbreviate lithium's electron configuration. All right, the full electron configuration for lithium is 1s2, 2s1, but helium is 1s2, so I can abbreviate lithium using helium's electron configuration plus that additional 2s electron. In this case, it didn't really save you very much writing, right? But when we get to one of our larger elements, it's going to be very convenient to use this noble gas abbreviation. All right, so let's do another one here. Let's do aluminum, and then let's do one of these D block elements because we haven't done an example from there yet. Let's do aluminum and zinc. No, screw it. Let's do a bigger one. Let's do aluminum and cadmium, CD. All right, so I'm going to kick this off the same way I did before. I'm going to find my element on my periodic table. This tells me that the last orbital in aluminum's electron configuration is 3p1 because it's the first element in the third row of the p block. And then I got to include everything that came before it. So what's right in front of 3p, if I jump from element 13 to element 12, now I'm at the 3s row, so 3s2. But then in front of that, if I look what's in front of element 11, now I get to my noble gas neon, so now I can just say insert whatever neon's electron configuration is. All right, so if we take neon's electron configuration and then we add the 3s2 and the 3p1 will get ourselves to aluminum's electron configuration. So which noble gas, so cadmium, first of all, on our periodic table is down here, the last in the 4th row of the D block. All right, so what noble gas am I going to be using for cadmium? Krypton, the next smallest noble gas. I can't use xenon, even though that's closer, because xenon has more electrons. So I got to use the next smallest noble gas, which will be krypton. And again, I'm going to start this out the same way. I'm going to look where cadmium lives on the periodic table. The D block has a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows to it. Cadmium's the last one. Again, we start numbering the D block at 3, so this is the 4th row here. So that means the last orbital in cadmium's electron configuration is 4d10. All right, and what's in front of 4d? Be careful, it's not in numerical order here. What's this row right here? 5s. All right, so we kind of get knocked out of order here when we start introducing d and f orbitals. All right, so in front of that will be the 5s2. And then in front of 5s, now I'm at krypton, right? From element 37 to element 36. So now I can insert my noble gas. Boom. All right, so that's how we get our noble gas abbreviation. Okay, just to do one more here. Let's pick another one in that D block, but we're going to go even larger here to platinum. Okay, so I'm going to start this off the same way that we did before. Platinum is the 8th element in the 5th row of the D block. So that last orbital would be 5d8. Okay, but when I look at what comes before that, we have to be careful. If we look carefully at our periodic table here, we jump magically from element 57 to 72. All right, what happened to element 58 and 59 and 60 and all that jazz? That is our D block down here, or I'm sorry, our F block down here. Okay, so periodic tables are sort of cut up like this because it's more convenient to fit on the page. And honestly, we don't really use these bottom elements very much. They're very, very rare. So we kind of take that F block and we move it down so we can scrunch everything together. But really what we should do is in this periodic table, let me actually kind of get rid of some of these markings so we can see this more clearly. My periodic table, what should be right here, inserted between this. We'll crack our periodic table at that line and we would insert that F block. And so you'll see these periodic tables sometimes, not in this condensed form here, but with this F block inserted right in there. So it's much wider, much more spread out. Okay? The bottom line is that when we move on to our next orbital here, what comes in front of the 3D, again, if we look at our atomic numbers, 72, we need to include this right here. All right, and this is our F block. We start counting our F block at at row 4. So let me just get my markings back here. So what goes in front of 5D is actually the 4F. Okay, and if we count how many electrons can fit in that 4F row, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons total. So 4F, 14. And then what's in front of that F block now? I'm back to normal here. I got now my 6s2. And then I can use my noble gas abbreviation. because what's in front of that 6s row would be my noble gas xenon. Okay, so this is only going to be relevant for elements that are in these last two rows of our periodic table. But you got to know that right here, if we were to draw out our periodic table, we need to insert that F block. Okay? Now, truthfully, with regard to this F block here, I would not ask you what the electron configuration of, say, europium was, because the filling in of this F block has just more exceptions than they do elements that follow the rules. So we're only going to deal with elements that are in these, maybe the D block or the P block in this row here that would have full F blocks. All right, but nonetheless, we need to know that if we pick an element, for example, mercury, we would have to have that full 4F in its electron configuration. All right. So now we're going to move on to what are called electron configuration diagrams. And this is just taking that same piece of information, but making this little plot on with it. And there's actually a little bit more information that we get from the plot than we do just by looking at it in that linear form. All right, so we're going to use as an example here oxygen, which has the electron configuration 1s2, 2s2, 2p4. And we're going to translate this same information into this plot, into this diagram. All right, so step one, we're going to draw our y-axis, which is energy. Okay, so we're going to be plotting these orbitals from increasing energy here. So I'm just going to make a chart with a y-axis, and I'm going to label that y-axis energy. All right, so then we're going to put on our diagram here, we're going to draw our orbitals from lowest to highest energy. All right, so we're going to draw these orbitals on this diagram here from lowest to highest energy. Importantly, that's the way in which we drew them in our electron configuration. So the orbital that we list all the way on the left here, that 1s, this is the lowest energy. And all the way on the other side, that 2p, this is the highest energy, right? So that's the order in which we list them. When we learned how to draw our electron configurations and we put those orbitals in a specific order, we put them in from lowest energy to highest energy. Those electrons that live in that 2p orbital have a higher energy than the electrons that live in the 1s orbital. So I need to draw my 1s orbital on my diagram here. So how are we going to do that? We're going to make little boxes. Our s orbital will just have one box. Our p orbitals will have 3 boxes. And our d orbitals will have 5 boxes. So then, given this pattern here, what do we think about our f orbitals? 1, 3, 5. What's the next number in that series? 7. Okay, so let me show you what I mean here. We're going to start with our lowest energy orbital, that 1s orbital. And since it's an s, we're going to draw one box to represent that 1s orbital. So at the very bottom of my diagram, my lowest energy on my chart, right? My y-axis is increasing energy. So at the very bottom of my chart would be the lowest energy orbital, and that's our 1s orbital. What's going to be next on this diagram? The 2s. And how many boxes am I going to draw for that 2s? Just one box, because it's an s orbital. It's higher energy, and as we discussed, that principal quantum number means it's a larger sphere, but it's still an s orbital. It can still, it's still only going to be one box. And then my next in line here is which orbital? 2p. All right, and for 2p, I'm going to draw 3 boxes. Cool, so now we have the shell of our electron configuration diagram. Now we have to go and we're going to fill it in with these electrons. All right? We have 2 electrons to fill into this 1s box and 2 electrons to fill into this 2s box. How many electrons are we going to fill into this 2p row here? 4, because there are 4 electrons in my electron configuration. Okay, cool. So we have these filling rules that we have to follow. When we fill in these diagrams, there are these 3 important rules that we have to follow. Okay. So 3 we're going to fill in with electrons following these rules. All right, so first we got to fill from lowest to highest energy. Okay. This is what's called the off-bow principle. It's a really weird name. All right, so which orbital am I going to start filling in first? The 1s, from the lowest energy to the highest energy. Okay, so to fill this in properly, we need our next rule. We can only have 2 electrons per box. One is going to be what's called spin up, which we represent with this upward pointing arrow. The other spin down, which is this downward pointing arrow. All right, and this is what's called the Pauli exclusion principle. All right, so when I fill in that 1s box with these 2 electrons, I can only fit 2 electrons per box. I only have 1 box anyway, all right? But when I fill it in, importantly, one of these electrons is going to be represented by an arrow that's pointing up, what we call our spin up electrons, and the other is going to be represented by an arrow that's pointing down, our spin down electron. 2 electrons per box, one's got to be spin up, the other spin down. They can't be both pointing the same direction. I'll discuss what spin is here in a second. Let's worry about how we fill in this business. All right, so how many electrons am I going to put in that 2s box? 2, all right? And since it's only 1 box here, one of them is going to be spin up, the other one's going to be spin down. And when I get to that 2p row, I got 4. Okay, so now we need the last one of our filling rules here. This one's very important to keep in mind. All right, we're going to have half fill all equal energy orbitals before going back and doubling up. And this is what's called Hund's rule. All right, so that sounds kind of weird, but if you look up here, I think it'll make more sense visually. All right, all 3 of these P boxes are at the same energy level, right? They're all on the same point on my y-axis. So when I fill in these 3 boxes here, what I'm going to do is I'm going to go through and half fill all of these boxes first, meaning put just 1 electron in there. I have 4 to use up. But I'm going to go 1, 2, 3. I'm going to go and half fill everything. And then if there's anything left over, in this case there's that 4th one I need to put in, then I'll go back and start pairing things up. All right, so we half fill our orbitals first, then we'll go back and double up if they are at equal energy, meaning they're all sitting in a line on that y-axis. All right, so my electron configuration here, my electron configuration diagram for oxygen represents the same thing that we have in our linear electron configuration, but represented in this diagram form. All right, and in particular, I can see that oxygen has 2 unpaired electrons. And it's a little bit out of the scope of this course, but these number of unpaired electrons have a lot to do with the chemistry of those particular elements. And you can't get that information just by looking at this linear electron configuration. You have to make that diagram, right? So there's just this extra piece of information when we take that electron configuration and we plot it, or we make this diagram giving us the number of unpaired electrons. All right, so we'll practice this with another element, but let me just talk for a second about spin of electrons. All right, and this is a phenomenon that's not actually unique to electrons. You find it a lot in different particles throughout the universe. But they have this property called spin associated with them, which really means that they have angular momentum, which is a fancy way of saying that as they're traveling through space, they're spinning around like tops, right? So electrons, as they're traveling through space, they're actually making this like corkscrew motion as they're moving. They're constantly spinning around as they're traveling through space. So this angular momentum means that they're spinning around like tops, right? Like those little toys that you take and spin them around and they continue to just go and go and go. That's what electrons are doing. All right, and we just have this fancy terminology, spin up. Means that these ones are spinning in a certain direction. Let's just say clockwise. And spin down means that those electrons are spinning in the other direction. All right, so for example, if we take a 1s electron, Remember that s orbital is a sphere, and we think of these orbitals as electron cages. So these electrons are trapped in that orbital. We can fit a max of 2 electrons in that orbital. One of them, as it's traveling through space, it's moving around this orbital here, but it's not just moving in a straight line. It's doing this little zigzaggy thing as it's going, or not zigzaggy, corkscrew thing. It's spinning around as it's moving. The other electron has to then be spinning in the opposite direction. This is another one of these bizarre things that scientists, nobody really thought that this was going to be the case. It wasn't until quantum mechanics came along and predicted this phenomena, and then later they built these very fancy pieces of equipment where they could actually measure the spin of electrons. All right, this is just this weird property that comes out of the quantum world. Many particles, for our purposes, really the only ones we care about are electrons, have angular momentum, which means that as they're traveling around through space, they're also spinning like tops. All right, and it just so happens that in an atom, we can fit 2 electrons in the same orbital as long as those electrons are spinning in opposite directions. All right, so then let's take this same idea here, but let's build an electron configuration diagram for a different element. All right, we're going to pick silicon. And the first thing that we need is that actual electron configuration. Before we can make a diagram out of it, we have to get our electron configuration. Silicon is located right here, element 14 on the periodic table. So everybody take a second, get that electron configuration, and then see if you can't translate that information into an electron configuration diagram. All right, so I have my diagram here. I have this arranged from lowest energy orbital down on the bottom, my 1s, to highest energy orbital up here at the top, my 3p. And I have to fill this in with these electrons. My 1s orbital is fully filled with those 2 electrons, 1 spin up and 1 spin down. Same thing with my 2s. My 2p is also fully filled, but if I'm being really good, I'm going to fill it in a particular way where I go through and half fill 1, 2, 3 before going back and doubling up 4, 5, 6. Right? We half fill our orbitals of equal energy first, and then we go back and double up. Because it's fully filled, you can't really tell, all right? But I'm just being really good with the way that I'm filling these in for practice, because it will matter when I get to the tippy top of this diagram. So my 3s is also full with 1, 2. And then I get to my 3p orbital, and I only have these 2 electrons. So again, importantly, I'm going to go through and half fill first, and now I'm run out, right? I'm run out at these 2 electrons. So here is my electron configuration diagram for the silicon atom, which has these 2 unpaired electrons. Cool. So we can take that same information that we were learning about last time, these electron configurations, and we make these diagrams out of it that help us picture that information as well as give us a little bit more about the number of unpaired electrons in a particular atom. All right, and then the last thing we're going to note here today are our electron configuration exceptions. All right, there are a few elements on the periodic table that do not obey our filling rules that we've been talking about, do not obey our rules for constructing our electron configuration. It's not too bad, but there's a slight little twist on there. All right. And the reason for these exceptions is that half-filled orbitals and fully filled orbitals are extra super stable. All right, so let me just give an example here. We did oxygen's electron configuration. Whoops. And we made this diagram. All right, so this was our diagram for oxygen. If we made the same diagram for nitrogen, which just has 1 fewer electrons, it would have 1 less in that 2p row. If I did that same diagram, but for nitrogen, this would be my electron configuration. All right, just 1 fewer electrons. Nitrogen's 2p orbital is half filled. All of these orbitals all of these boxes just have 1 electron in them. So that means that this electron here is harder to remove than oxygen's electron, because oxygen does not have only a half-filled orbital. It's got 1 extra. All right, so there's something that's like extra special stabilizing about having an orbital that's exactly half-filled or exactly fully filled. It's harder to remove an electron from a half-filled or a fully filled orbital. And so that's what we're going to see our exceptions come from. Okay, all of our exceptions are D block elements. all right, and specifically ones where you would expect their electron configurations to end in either D4 or D9. All right, so that's going to correspond to specific rows on our specific columns on our periodic table. All right, so we can sort of visualize where these exceptions are. They all live on a particular place on our periodic table. Let me just get rid of these markings so it doesn't get too crazy. They're either in the 1, 2, 3, 4th row of the D block. So these are all exceptions here. Or the 5, 6, 7, 8, 9th row of the D block. So these two columns here, I'm sorry, I keep saying row, columns of the D block, right? So these two columns here are exceptions to our filling rules. Okay, so what we would expect, for example, chromium's electron configuration to be would be argons plus 4s2 3d4. Okay, so let's just visualize this here with our diagram. Whoops, geez Louise. All right, I'm going to be lazy and only look at this top one here. We'll say whatever argon is lives down here. I got one box for my 4s electron. So we're going to do the noble gas abbreviated diagram here. Jeez. Okay. So here's my 4s. And how many boxes should I have for my 3d? 5, right? So now d orbitals have a total of 5 boxes. All right, so fill this diagram in based on that electron configuration and our filling rules that we discussed. Go ahead and fill in this diagram for the chromium atom, what we would expect its electron configuration to be. All right, so what we would expect is for chromium to have a fully filled 4s orbital, and then 1, 2, 3, 4 electrons in its 3d. But again, there's this extra stability that comes with having a half-filled orbital. And it's so close, it's only 1 electron away. All right, so instead of having a fully filled s and this not half-filled d, chromium instead rearranges these electrons so that everything is half-filled. Right? It's got a half, it's going to take this electron that used to be in that 4s and move it up to that missing spot in that 3d so that everything is half-filled. So it gets that extra bit of stability from that half-filled d orbital. So the actual electron configuration for chromium is whatever argon's is plus 4s1 3d5. All right, so we said that our exceptions are these D4 and D9 ones. You will never have an electron configuration that ends in D4. Instead, it will have just one electron in its s orbital and 5 electrons in its d orbital. Whatever number that s is, that d orbital is going to be 1 less. So let's just do an example. I feel like it's going to be easier than variables here. So 4s, not 3d5 instead of ending in d4. And same thing with d9. Instead of getting a half-filled d orbital, this will give a fully filled d orbital, but it's the same idea. It's going to take an electron away from the s orbital in order to fill up that d orbital completely. So for example, copper will have the electron configuration with 4s1, 3d10 instead of the expected 3d9. All right, so our exceptions are these elements that live in the D block where we would expect them to end in D4 or D9. You'll never see an electron configuration ending in D4 or D9. Instead, you're going to take one away from the s orbital and add it to the d orbital. All right, so these are these exceptions. Again, they all live in these same columns on our periodic table. We can just put our actual here. Cool. All right, we'll finish this up next time.